So our next speaker on formal verification is Professor Tom Mellom from University of Oxford, where he's the Professor of Computer Science and has worked in the field of formal hardware verification since the early 1980s. His research is aimed at practical application. He collaborates closely with leading companies in EDA and semiconductors on advanced tools and methods for formal verification. And his topic is end-to-end formal verification of processors with fine-grained memory protection. Thank you, Tom.
Thank you very much. Thank you. It was mentioned that I've been working in formal since the early 1980s, and cast my mind back to that time. They all thought we were crazy, that this would never succeed, and it's been absolutely wonderful to see over the years kind of steady progress in the field, and this is now a practical technique. So what I'll be speaking about this morning is a student project at the University of Oxford, applying formal verification, kind of the kind that Tobias talked about just now, to a new kind of processor architecture that's the subject of a large research program in the UK, and I'll tell you about our results in this case study. So the architecture is the so-called CHERI architecture, which is a processor architecture designed to assure essentially memory safety by quite an old idea of capability in addressing. So memory addresses in this architecture get replaced by so-called capabilities. So capability, as you see in the picture here, as an address, but it also carries around metadata about what that address can dereference. So a region of memory within which the address may be used, as well as some permissions about what you can use the address for. Can you jump to it? Can you read? Can you write? So permissions, as well as a kind of region. And critically, capabilities are tagged with a hardware tag. They're implemented in the hardware, and they're tagged with a hardware tag that guarantees their provenance and validity. So you cannot forge a capability out of nothing. They can only be created in kind of regulated ways, and this is what assures memory safety of software running on top of this architecture. So to use a capability, it has to be in a register. Capability provenance is maintained by the architecture. So at the beginning, an omnipotent capability that it can address anything is created by the hardware, handed to the operating system, which then can hand out, restricted parts of that capability to the rest of the software stack that's running on top. So you can change the bounds of the address, but you can only narrow them. You can change the permissions, but you can only make them less permissive. So all non-increasing properties. This is the so-called monotonicity property of this architecture. And any invalid operation, such as having an address that is used to dereference memory outside the bounds, clears the tag and results in an invalid capability that can't be used. So in some sense, execution here is confined to access only kind of the transitive closure of capability registers, which you have. Okay, so this is a capability. The early representation of this was really quite generous in the size. So you have a 64-bit address, but then you have three other 64-bit words, which give the base and the length of the size of the region that can be accessed, some permissions, some typing information, and so on, and a tag. So this original representation was really heavy on memory and cache and bandwidth, and so a very rather clever, and this is not to do with us, but Cambridge researchers developed a rather clever compressed form of capability, which is a kind of an encoding that has some resemblance to floating point, a floating point representation. And I love that because I'm, one of my things has always been a floating point verification, which I love to do, right? So I was really excited to work on this. But from a formal verification perspective, it's kind of like there's floating point data all over the processor, right? So you've got this compressed capabilities everywhere. You can't use them without decompressing them. So you need sophisticated microarchitecture to do that fast. You need caching, all kinds of stuff changes inside the processor when you have this. Just a word about one of those things. So not with this compressed instruction representation, not all combinations of addresses and bounds are actually representable. So representability has to be checked with some kind of pointer arithmetic. And you have to do, the specification for the processor has representability checks all over the place, right? And those have to be either limited or somehow worked around or microarchitecturally optimized in the hardware. Bounds checking, by the way, is done when memory is dereferenced. So you can push your address outside the bounds, inside the processor. There's no problem. But when you try to read or write from memory, or do a jump, then that's when the checks happen. Okay, so we've had a little series of projects in Oxford on student projects on formal verification of CHERI processors. So why should we do this? Well, this is a hardware assured security technology, right? So unless our processor designs maintain that monotonicity property and are correct, then the entire stack, of which there's a large stack that's built on top of CHERI, is on unfirm foundations. So it's really important to get this right. I'm at a verification conference. I don't have to preach verification to you. So we've done 2 processors so far in increasing order. And what I'm talking about today is this Chariot IBEX CHERI processor, which is an extended version of low-risk's IBEX RISC-V processor with the CHERI instructions. So this CHERI ISA comes with a whole bunch of specialized instructions over capabilities, and this is an extended version of IBEX with those instructions. And that's what we used as our case study. So these are some of our principles in this. So we are going for full coverage of the entire ISA. We're covering both CHERI and the RISC-V part. We want to make no formal verification-driven modifications to the specification. And the specification here is written in a language called SAIL, which is an ISA specification language, a little bit like ISA formal, which some of you know about. And that's actually an official RISC-V specification written in SAIL. And there's a CHERI RISC-V specification also written in SAIL. We wanted to make no changes to that. We'll want complete proofs, not bounded proofs. So we're going for complete proofs. We want them to be as end-to-end as possible, so not 500,000 tiny properties, but big properties that show execution end-to-end. And we would like regression to be as fast as possible. So we would like our instructions to verify in minutes, not hours. Someone mentioned earlier today, I think we have infinite time because we're working in the university. So that our secret weapon is infinite time, right? Okay, so some outcomes of this project. We found numerous bugs, some of them serious. We have higher confidence in the correctness of this design. We've developed some new methodology and tools, and of course, we're publishing a paper. Hopefully, we can open source the verification code. That's still to be determined. But really, we're moving in the direction of more difficult CHERI processors, and eventually, we're looking for some kind of configurable proof kit based on the principles that we're developing that might extend to RISC-V a little more generally, and maybe integration of this SAIL language in some way into industry EDA flows. So just say a little bit about SAIL. So this is SAIL's developed in a project in Cambridge. There's a huge SAIL ecosystem here, which you see on the slide. Lots of SAIL tools, but it was never really designed for sort of downward-looking specification of processor ISAs. It was more about what does the instruction set do, so that you can reason about the properties of software or generate tests or all that kind of thing. So there was nothing in the SAIL flow that allowed us to use a SAIL specification as the reference model for a verification. So our friends in Cambridge, in collaboration with us, developed a SAIL to Verilog flow by tapping into some existing part of this complicated bunch of flows, basically an SMT flow. So we've now got a mapping from SAIL to Verilog, and then of course we can read the Verilog into industrial class formal verification tools. So this really allows SAIL specifications to be used with leading edge tools. And when this came along, we didn't have this in the previous project, and this transformed our productivity, right? Because we didn't have to spend time on the specification. So this is a great start here. What are the results? Well, we found about 25 bugs At least 4 of those bugs break this crucial monotonicity property of the architecture. So they allow capabilities to become more generous, which is not supposed to happen, and so that's a security violation. At least one of the bug has a software exploit, a little bit of a slightly fanciful software exploit, but I think it's reasonable, right? And through Formal, we also had quite an extensive discussion with the designers at Microsoft of what exactly is a valid capability, which hadn't really been completely formalized. And so here's a list of some of the bugs we found. Okay, so progress to date, all the CHERI memory, all the CHERI instructions memory, some of the RISC-V instructions verified with fully conclusive unbounded proofs. And here's a list of the things that we verified. And these, my main verification engineer would just not stop until these proofs were regressed fast. We've got fetch checks and instruction fetch correctness. We handled that separately. IRQ checking. What we haven't done, there's some shifts that should be all right. We've got the multiply and divide, which I'm rubbing my hands over because I know what to do with those, right? Probably switch to symbolic trajectory evaluation for that part of the architecture. Some other instructions. WFI, unclear what we're doing there, but we're not going to stop until we've finished as much of this as we can. Then there's always the question, how do we know we've proved everything? So we'd like to wrap all of this up, and we are using a case splitting on instructions, of course, and so on, which is a great methodology in this area. But we'd really like to combine all of those results to have some global correctness property that says this is correct, and we know we've proved everything. And I think that'll be some form of trace equivalence, if you know what that means, between the sale specification and the processor overall. And of course, next, we always aspire to verify the operating system and the software stack on top. We did a little bit of work on machine code verification. It didn't end happily, but that that's always a gleam in my eye. But I seem to be continually dragged back into verifying the processors. We have lots of the sale to Verilog compiler is open source, and you can get it from the sale repo and play around with it. The Verilog produces very ugly and huge. I mean, if you load the whole specification into Jasper, it takes about 20 minutes just to elaborate, right? So that's not great, but we have lots of ideas for how to make that compilation flow much more efficient, and here are some of them. Debuggability is not addressed yet, and so it's quite hard to debug, but we have ideas there too, and how to deal in the longer term with the configurability of RISC-V in a specification is an interesting question for these kind of specification languages, because they don't cope with that very well. This is a completely AI-free project. We used human intelligence for this, and here are my wonderful students who worked on this. And I want to emphasize, these are all either new graduates or were current undergraduates working over the summer or in their, alongside their courses while this project was carried out. And so for me, just going back to 1983, we would never have dreamed that we could do verifications, without a PhD, right? And so this is my secret intelligence behind the verification. And I was reflecting a little bit about why in some sense we succeeded with this. And I'm not saying this is a scalable solution for the companies out there, but every undergraduate in Oxford is taught about invariance in the very first year, and they're taught about proving the correctness of code in their very first year. And so finding design invariance manually was our way of pushing this thing through. And I can see heads shaking already, but that is really what the work was here. And AI maybe will be helping us do that in the future. So I think that's a very interesting thing for all of us to be thinking about. So thank you very much.
Thank you. Thanks, Tom. Thank you very much. We've got some questions. Yeah, before you dash off. Any questions from the audience? Tobias?
So we actually tried to find the system, Sail to Verilog compiler, funny thing, 4 weeks ago. Is that a new release or did we just not find it?
You didn't find it. So just email me and I'll point you to where it is.
Nice.
It's there still. Right.
Second question. What's your idea on, okay, I know the EBEX, we have it also as a demonstrator. There you can just run the proofs raw, it will converge eventually on EBEX. But if you even look at the regular, whatever, dual issue 6-stage pipeline, like, what's your idea to make that converge? Because that's much harder. And that's still like a small processor.
My idea is to get some more undergraduates and run another project in next time. So and this process is very simple. It's no out of order, it's no dual, so
exactly.
Yeah,
the undergraduate invariant machine that is a good one. Yeah.
So we'll do that. But I'm very happy to kind of share with what we have.
Start of your activity. Eventually evolve.
Yeah. Eventually we're.
Okay, there's a couple of questions online, so I'll move to them. Tom, what is the main limiting factor for the scalability of these methods?
Well, so we spent a lot of time on making regression fast, and that was done, and also getting complete proofs, and that was largely speaking done by human intelligence finding invariants and proving invariants that would assist in proving the end-to-end properties. And so the limiting factor there is the skill factor of people who know how to efficiently postulate and find invariants that will move the proof along. But it's just the world is full of skilled people, and there's no reason that our verification engineers can't be doing some of that in the future. And one of the things we did here was a lot of proof decomposition.
Okay.
Assume guarantee, abstraction. It's kind of the opposite to push button verification. It's verification where you really get intellectually involved in why the thing is working and guide the proofs that way. And I think scalability is good. We have to have good tools that help us, and maybe AI will help us with that as a kind of co-pilot in the future.
Those assumed guarantees are quite difficult to identify and
yeah. Assume guarantee. We have an induction in there.
Okay.
So it's yeah.
Brilliant. Okay. Thank you very much.
Right. Thanks.